So hi everyone, I'm Dina. Let me just give a very quick overview of the overall domain adaptation setup. So in this challenge, we propose a large-scale synthetic source data set for industrial waste sorting. So here we focus on the segmentation of recyclable objects. And along with a synthetic data set, we propose a smaller scale real data set with semantic segmentation. And the challenge for this task is to use the synthetic source domain and the label's real source domain to adapt the segmentation model to the unseen, unlabeled target domain. First, let me briefly talk about why we believe that automation of waste sorting is crucial. And I'll start with the different kinds of waste management strategies. So the most common ones are, first of all, landfill. This is the most environmentally unfriendly and the most common option in most countries, including the US. Next goes the incineration or burning waste. It's a slightly more environmentally friendly option, but it still contributes a lot to the pollution. And finally, recycling, which is the most environmentally friendly and the most technologically involved option. In this challenge, we use the data that we collected in the United States because the United States is the leading country in terms of the amount of waste produced by volume and the amount of recyclable waste produced in the US grows rapidly with each year. In fact, this year, US produced more than 800 kilograms of solid waste per person, out of which less than 25% have been recycled. US is ranked 25th in the countries in the Global Waste Index this year, so there is clearly a lot of room for improvement. The reason for this inefficiency is that consumers are asked to store recyclable waste of 4 material types in the same bin, and then the recyclables are collected and sorted at a material recovery facility, or MRF. MRFs operate in a semi-automated fashion, meaning that they have a lot of machinery involved, but this still heavily relies on manual labor. Here you can see a typical example of the sorting process in the MRF. As you can see, this is a very physically demanding, challenging, and sometimes dangerous task for the workers. We believe that automation of waste sorting is crucial to slow down the pollution and to make waste sorting more efficient and profitable, and most importantly, to make this waste sorting a less mundane, dangerous, and physically demanding task. Why do we think that domain adaptation is very important for waste sorting? Because waste sorting data can vary significantly depending on, for example, where you collect the data, or in what season was the data collected, or, for example, what kind of machines does this specific MRF use? Not to mention the data collection setup itself, for example, what kind of camera we have, where did we place the light source, and so on. In addition to that, annotation of the new data is prohibitively expensive for this task. So we conclude that it isn't feasible to collect a gold standard data set for the waste sorting application, and it needs to be continuously updated. So the solution must be able to adapt continuously in a label efficient way. Here I will give a very quick overview of domain adaptation for those who don't know about this task. Suppose we have a downstream task. For example, we want to classify cats and dogs, and we have a really nice labeled data set for this. So we train our model, and then we evaluate this model on a test set, and it works really well on this data set. However, if we take new examples that are semantically similar, but are visually different. For example, here we also have images of cats and dogs, but they are visually very different from our examples from the source domain. And if we just simply evaluate our model on those new examples, it will most likely perform poorly because of the so-called domain gap between the images in the source and target domains. In domain adaptation, we aim to use the labeled source domain examples and the unlabeled target domain examples to adapt our model to work well on this new unlabeled data. Simply speaking, we want the source and target domain features of our model to roughly come from the same distribution. Thankfully for our application, there is a publicly available data set called Zero Waste that we published this year, our lab published this year. Zero Waste consists of more than 4,500 fully annotated examples where we did polygon annotation of objects of four material types: cardboard, soft plastic, rigid plastic, and metal. Even though Zero Waste is a high quality and real in the wild data set, it has a limited diversity because it was collected at a single MREF. To overcome this limitation, we propose a synthetic data set that we call SynthWaste. We generated SynthWaste specifically for this challenge. The advantages of synthetic data are that, first of all, it's cheap and easy to collect and annotate the synthetic data sets. And synthetic data allows control over the simulation parameters. For example, the position of the camera or lighting, clutter level, and so on. The biggest disadvantage of the synthetic data is that it introduces a significant domain gap with respect to the real examples. So it is a challenging domain adaptation problem to adapt the model from synthetic to real domain. To further increase the diversity of our synthetic data set, we augmented our data with style transfer. Here you can see an example. So we randomly selected instances or objects in our frames and used style transfer with the corresponding material types. So just to recap, our overall setup is we use a large-scale synthetic source domain data set, SynthWaste, and a smaller scale real source domain data set, Zero Waste. And we propose to use those two labeled data sets to adapt to the new unseen and unlabeled data that we collected at a different MREF in a different time frame. Jumping forward, I would like to say that our winning team's solution managed to beat the baseline by over 7% MIU, which is very significant for this task. And I would like to also mention that this setup is significantly different from the standard simulation to real domain adaptation setup, in a sense that, unlike in the previous challenges where they only use synthetic data as a source domain and only use the real data as target examples, here we propose to augment a real source domain with synthetic data. So this is the sixth iteration of our VisDA challenge, and we adapted most of the rules from the previous iterations, but we added a few new rules here. First of all, in this challenge, we allowed teams to use any publicly available data sets to train their models, except of course for the target domain examples. We didn't allow them to label them or to somehow use the labeled data. And we made sure that all the winning team solutions are reproducible, and we placed the responsibility on the reproducibility aspect on the winning teams. And just like in the last years, we to promote the fair competition and to not give unfair advantage to the larger institutions and companies, we limited the total number of parameters to 300 million parameters total. The winning solutions are determined based on the MIU on the test set of the target domain. And finally, to avoid overfitting to a target domain, we set the limit on the number of submissions in the test phase to 5. Here you can see some statistics about our challenge. We have 14 teams participating in the development phase with more than 300 submissions, and 8 teams participating in the test phase with more than 40 submissions. And I'm happy to announce our winners. So the first place goes to Team SI Analytics from Hanbad National University. Second place goes to the PROS team from Tel Aviv University. And the third place goes to BITDA from Beijing Institute of Technology. Our key results for this challenge are, first of all, that the DA format that we used for as a baseline turned out to be a very strong baseline. In fact, only 4 out of 14 teams could beat DA format in the development phase. Only 3 out of 4 could beat it in the test phase. The results from the winning teams show that some forms of self-training and various types of augmentation proved to be the most efficient for our task. Excuse me. Finally, we found that the winning team's solutions didn't end up incorporating synthetic data in their solutions. This is due to the fact that synthetic data introduces the large domain shift with respect to the real waste sorting data. And we are looking forward to see future work that could efficiently utilize synthetic data to further improve the performance on this task. Excuse me. Finally, I'd like to say that all the data and the code we used for this challenge are available on our GitHub page. And we successfully reproduced the results of the winning teams, and the official code for the winning solutions will be available on our GitHub page shortly as well. Thank you, everyone. And I'm giving it over to Samart.
Thanks, Dina. So next up in our schedule, we have presentations from winning teams. But before that, let me note a couple of things about the talks. For the audience, you can type questions in the chat during the talk, and we can take those questions up at the end of each presentation and ask them to the speakers. So for the challenge participants, we have up to 3 minutes of Q&A. And for invited talks, let's keep it to 1 to 2 questions right after the talk. And others we can take at the very end in a final Q&A and discussion session. Speakers, you may please expect 2 reminders from me, possibly via Zoom chat, one like a minute before the end and another at the end of the talk duration, so that we keep things moving as per the schedule. All right, so without further ado, let me invite the first team, SI Analytics. And I think we have Dehan Kim here to present on their behalf. Dehan, you may start sharing if you're here. Oh, I'm sorry. Yes.
Can you hear me?
Yes.
Okay. Hello, I'm Dehan Kim from Hanbad National University in South Korea. It is a great honor to be present here. Today, I'm going to talk about bag of tricks for domain adaptive semantic segmentation. I will proceed in the following contents. This year's VisDA challenge discussed a very important social issue. That is an industrial waste sorting scenario. As you know, we can get the urban traffic and human-centric scenarios. However, it is difficult to collect the gold standard dataset in the waste scenario. It is because the target object visual appearance and contents are changed by time. This year's task is unsupervised domain adaptation for semantic segmentation. The source domain contains synthetic and partial real domain. And the target domain is 0 waste V2, which is the real domain. and it is cover all season and location. Here is the same setting as the unsupervised domain adaptation task. The model can only access images of target domain dataset. Under those conditions, the evaluation metric is mean intersection over union. The baseline provided by the organizer is DA former. And DA former framework is a very strong baseline that has achieved the state-of-the-art in benchmarks. In DA former, 4 training strategies are used for unsupervised domain adaptive semantic segmentation. The 4 things are transformer-based architecture selection, layer class sampling, thin class ImageNet future distance loss, and learning rates warm-up. We followed some DA former training strategies. However, 2 main things are different. First, we choose ConvNext architecture instead of the mixed transformer encoder in segformer. This choice is for using large-scale prior knowledge from public available ImageNet 22K pre-trained weights. Next, we removed the layer class sampling in DA former because VisDA dataset is different from common benchmark, such as GTA5 to cityscapes or Cynthia to cityscapes. This condition is same as the baseline, but we found that layer class sampling is invalid in scenario, and that did happen when the co-occur assumption is incorrect. This is an overview of the proposed method. Our key idea is a transportable representation, and it is from large-scale prior knowledge, such as ImageNet 22K. It is a method we used. Specifically, Donghyun Kim et al. Found that some important factors affect downstream tasks, such as domain generalization and domain adaptation. As you can see, the mainnet painting in the figure, changing the network architecture and using ImageNet 22K are more effective than using standard LegionNet 101. Most importantly, this approach is better than previous method without target domain dataset. We used the ConvNext architecture design to use transportable representation from this study. Also, we use a moderately deep ConvNext large backbone for accuracy and efficiency. As a result, we achieved about 58 MIOU, which is a large difference from about 52 MIOU in the DA former baseline. Next, we use the model soup for more powerful domain adaptive performance. Model soup is known for improved model performance and robustness. Model soup can produce a better model. It averages the weights after multiple fine-tuning without additional computation and inference time. So we adapt model soup using pseudo label in our solution. There are 3 augmentations used in fine-tuning: photometric distortion in segmentation, Gaussian noise in argumentations, and random grid shuffle in argumentations. The fine-tuning process only trained 10K iteration first, and then multiple fine-tuned weights are used with initial UDA weights as a model soup recipe. Next is performance and results. This table shows the stepwise model performance in our solution. As I mentioned earlier, we used the ImageNet 22K free chain weights and changed the network architecture. With this simple approach, the initial UDA model shows outstanding adaptive performance. Also, fine-tuning model using various segmentation achieve additional performance improvements. The 4 weights are used the model soup recipe. After model soup performed, the final model shows the best performance. The most impressive result is source-only setting, because in source-only we did not use the model soup. We show the qualitative results of our solution in the following. Briefly, we've got that 2 points are efficient and powerful in unsupervised domain adaptation. First, using domain transportable representation from modern pre-training is more effective in the task. We improve the performance with the simple changes, and it is much better than the general benchmark, which improve under 3 MIOU. Second, the model soup is also improved the performance in the domain adaptation task. If you want to advance the model with the simple method, thus 2 approach will be the best choice. You can see the more detailed information in our archive paper. This is our references. Thank you for listening to my presentation.
Thanks, Jehan. Do we have any questions? Again, feel free to type it in chat even now, or since I don't think we have too many people, you can feel free to unmute yourself and ask a question. If not, I guess I do have one. Could you speak a bit more about the specific augmentations you used for the 3 branches of your model soup? So what specifically is photometric distortion and random grid shuffle, I suppose?
Oh, yes. We've got considered the other 5 augmentations, except present this slide. Motion blur and optical distortion and the other, but the best combined augmentation was photometric distortion and random grid shuffle and Gaussian noise. Yes.
I see, and I think the name suggests what the specific distortions are. We have another questions from Shahaf in the chat. Did you use this method also on autonomous vehicles tasks? You could let us know if there's. If you'd like the question to be elaborated or something. Okay, go ahead. Sorry.
Remove the random grid shuffle. If you remove the random grid shuffle, it is used for autonomous vehicle task.
I see. Any other questions, any follow-ups or anything? And if not, then we can move to our second place winners.
Quick question.
Sure.
Probably a question for the organizers. In terms of the evaluation metrics, mean IOU and pixel accuracy, are those the two metrics that was being used to compare all the submissions?
Yes.
Yes, so we used MIU for the main metric, and in an lucky event of a tie, we broke the tie using the pixel accuracy.
Got it. Thanks.
And just for complete elaboration, we had 4 classes over which the mean MIOU was computed. All right. So thanks again, Dehan. Nice presentation, and thanks for taking up the questions. Next, let me invite Team Pros, and I think Shahaf is here to present on their behalf.
Yes.
Why don't you go ahead? Thanks.
Yes, thanks. Can you see the presentation?
Yes.
Nice. Wait, I'm gonna switch. So, hi everyone, my name is Shahaf, and we were working together in Team Pros with Shadi and Aja, and we used the HARDA on industrial waste datasets for the VisDA challenge. So let's start. Actually, HARDA is a high resolution domain adaptation, which is a framework that was suggested by Hoyer et al. This method suggests multi-resolution training and scale fusion through learned scale attention in order to distinguish between global view or large images and fine little details in the image. And the choice motivation is clear. HARDA and the former backbone are the state-of-the-art method for semantic segmentation in UDA. So we took this method and combined the VisDA datasets with this method and tried to train and see what happens. So we did short ablation study with several different source data. As the organizer stated, the data sets were.
Excuse me, Shahaf.
I see. Wait, I will try to fix this. Tell me if you can see it.
All right. Yeah, we see the third slide now.
You see the first slide now?
No, not yet. It's still at the third slide.
Really? You see the first now?
Yes, first now.
All right. You see it by screen mode or it's full screen mode?
No, it's in
No.
the
And
we
now?
see your PowerPoint window.
And now?
No,
No.
still
Okay.
your window.
I don't know why, but we'll do the best here. All right. So as I said, this is the choice motivation, HARDA, I explained this. And the ablation study that we did contains several of data sets as proposed in the VisDA challenge, synth waste, and the zero waste V1. So we tried to combine a few combinations. The first one was only synthetic data, and the second one was to combine those two together. The third one was to distribute them both synthetic and real data equally, and because synth waste dataset has like 5 times more images than the zero waste V1. And the fourth one was to try to only using real data of 0 raised to v1. And additionally, as the previous technique showed us, we also try to ablate the RCS, which is the rare class sampling mechanism originally proposed in the former framework. So the results of this short ablation study showed that, as you already mentioned, real data is the most efficient and effective in order to adapt a new domain to the target domain, the source domain to the target domain. And also the RCS sampling did not achieve good results. I think it was mainly because the human error that is exposed in human annotation causes this mechanism, which relies on the rarest classes to be in this. So final results, we trained the HARDA using 0 waste V1 source data, and we see the validation and also the test improved the performance over the former as expected, and also over the original source domain. But let us see one more thing from the analysis that was already mentioned here in this session. The ablation study shows that using synthetic source data alone does not achieve good performance. Nevertheless, in the real world, annotated data is scarce. In most cases, is not available at all. For those common cases, we propose post-CST, which is an image-to-image translation method that boosts performance of UDA methods. We can see here, formally, the source domain, target domain gap that is caused due to the difference between both domains. We propose a different approach. We call it the SIT concept, where this concept can shorten the gap between source and target domain by using image-to-image translation between two different domains. We call the new data SIT, which is source and target, and we generate the new data and train the same method, the same UDA method on the new translated data. Our overview on the architecture is very, very complicated, and it is based on image pyramid translation, cyclic image translation, and also on style loss, adversarial loss, and cross-entropy loss. For more details, you can refer to our article and some qualitative translation example, so you can feel the differences. Here is the source domain, which was translated onto an SIT image, source and target. And this target image is translated here to target in source image in a cyclic manner. You can see that the appearance of the image is different, and the styles are matching the target domain, but the content is the same, which is very crucial property for succeeding in the semantic segmentation task. We've trained the domain, the validation and the test set using both SIT data and source data. We trained the same method, which was HARDA, and we saw an improvement of like 2.6, 2.2 when we used only synthetic data. We also used this very same technique on autonomous vehicle tasks, GTA 5 to cityscapes and Cynthia to cityscapes. And we've seen that we can improve state-of-the-art state-of-the-art UDA methods using our image-to-image translation. And by the way, this translation, the translation invariant to the method, which means the same set of translated images boosted all those methods together. So for a short conclusion, our team used the HARDA framework in order to adapt both synthetic and real source data to real data. We can clearly see that in our case, the synthetic data does not represent well the real world. Hence, the best performance achieved by using only real world annotated source data. And also, we've shown a new concept that achieves improved performance of generic UDA methods when only synthetic data is available. We believe that this concept can be extended to other types of problems where annotating images of a target domain is very costly. Any questions?
Great, thanks for the talk. Yeah, we can take questions either in the chat or feel free to unmute yourself and ask any questions.
I have a question.
Yes.
Thank you, Shah, for the presentation. Very cool work. Can you please go back to slide 10?
Yes.
If you look here at the first translated result, that the one that is near to SIT, one can notice that like there in the middle of the frame there is a plastic bottle or something like that, which was translated into a texture of the paper. Or does it just look like a bottle? It's hard to say because the light in here. No, the one slightly to the left, like the big.
This or this?
Below that one.
What did you say?
So like closer to the center to the left. Yes. Is there a way to point here?
This one, this thing, or this?
If you do want to just annotate, I think.
This. Okay.
No. I'm sorry. In the center, there's this round like object. Closer to the left, and I think in the source, in the original image, it was a plastic bottle. However, with your method, it was translated into a texture that is more similar to a paper one. So my question is, with your image translation method, I suppose it's working in an unsupervised manner, right? It doesn't use segmentation labels here.
It does use in the last scale. We combine the labels with the cross. I can elaborate from here. We use cross entropy loss in order to teach our generators to differentiate between different images, and we also do it cross domain. We teach one domain and the other domain. We put the loss through both generators. We call it the cyclic label loss, which was first used that we know
of. So basically what you do is you perform the translation, and then you segment the translation result, and you use the cross entropy loss to make sure that the segmentation of the translated image and the original image are consistent.
Yes, we combine, we encourage the generators of the translation to learn semantic properties. So in this way, we believe that we can push up the performance of any other method by only changing the images.
I see. I'm not sure I follow your method exactly, but I think there are papers that do something similar. I encourage you to take a look at works like Cicada or something similar.
But you can write down in the chat the names.
I will write in the chat.
Yeah, I will look at it also. Thanks.
Thank you. We have another question from Ehan regarding, okay, I'll read it out. Did you use HRDA? I think HRDA does forward pass multiple times, doesn't it?
I'm not sure you can use HRDA. I thought HRDA does fold multiple times. Well, no, I don't know what do you mean by multiple times. But we used the exact same. Why? I don't understand the question. I'm not an expert of how the details, what are the exact details of the forward pass. From what I read, it creates two scales, one which is large and one which is high resolution scale, and fuses them. I don't know what do you mean by multiple times. So can you elaborate?
Feel free to type or unmute and elaborate, Dehan.
And Dina, I now see that you refer to Cicada. Cicada actually tries to segment the images. Our technique does not try to segment, only to translate. And in our full article, we perform we take Cicada's images and we show that if we use them as we used, they output lower performance. You can look at the article if you want. It's in the archive.
All right. At this point, if there aren't any other questions or follow-ups, let's move on to our next participant to stick to schedule. Thanks again, Shah, for the presentation. Next, let me invite the team VisDA from Beijing Institute of Technology. I'm not sure who's here to present on their behalf. Can you please let me know? Is there anyone from team VisDA in the call? It may seem there isn't.
We can move to the invited speakers presentation, and while we do so, I will contact the VIT.
Yeah, although we should stick to the schedule we had earlier. So I'm not sure if we should like break for a bit or we could proceed. It's 15 minutes off. The concern being that if someone wished to join at a particular time for a particular talk, that would be off.
Maybe we can kill time with a couple of questions that I had.
Yes. Okay. Yeah, we can take more questions for the participants or even for us, the organizers, and we'll try and push it closer to the time we are supposed to start the invited talks. Thanks.
Yeah, just curious, like, do any of the choice of domain adaptation techniques have any sort of influence on the performance of the model on edge devices in terms of, you know, the resources that they consume and stuff like that? Was that a criteria at all? Is that of importance?
Definitely. There are two rules that concern efficiency and size of the models that we can use. So first of all, as I said, we limited the number of parameters that can be used in our models to 300 million. Mm-hmm. And one of the rules that I didn't talk about actually is the efficiency. So I think we limited the overall time inference time for methods, or training time I don't remember the exact amount of hours of GPU time.
We give them 100 GPU days. This is probably like over the limit you would consider. Well, edge devices, speaking of edge devices, I guess you would only be talking about inference on edge devices rather than training. Even 100 million parameter, 300 million parameters, which is our limit, is quite a bit above that. Yeah, in terms of this this challenge, I don't think it was a big consideration for models being able to be run on edge devices.
Got it. That makes sense. And I guess these solutions are all open source. And is it open sourced under a certain license for anybody to use it?
Not yet. So yeah, we'll point to the sources like soon on our webpage. Yeah.
I believe the winner, the first place winner has already made, you have already made your source code available. But yeah, we plan to release code. I also want to follow up on the edge device and efficiency. I mean, I don't think that these methods can run on something like a phone right now or a small device. But that is definitely something that's important if we are to implement them in the real world. We'll probably hear from some speakers later about how we could actually do this kind of recycling in the wild and in the real world. And, you know, the less power that these methods can consume, the better. But that wasn't an explicit constraint in this competition.
Got it. Thank you.
Are there any other questions to about the competition or to the first two winning teams from our challenge?
Maybe a general question about recycling. This is Subhrangshu here. So in countries who recycle much better than the US, do you know what they use? Is it some mechanical system or better initial sorting by people, or like there's some other combination of techniques being used?
I, of course, can't tell about all countries. I only know about a few examples like Germany and France, which are one of the countries in the top, that are ranked top in this global index waste sorting. And I think one of the main reasons why they are much more efficient is that they actually use the consumers to do most of the sorting. Of course, they post-process and they use machinery as well to separate and further increase the quality of the material they have. Yeah, if anyone else has any ideas about this, you know, we have a lot of experts here today.
Hey everyone, Amanda Mars from AMP Robotics. Happy to give the insight that we have from installing our technology across the globe, and excited to talk through what our technology is in a few minutes coming up. So yeah, there's policy that drives changes, there's consumer behavior that drives changes, and then there's infrastructure that drives changes. And so it really is across the board. For the policy in the EU, you know, EU and UK, now we have to say them separately, has long driven programs like extended producer responsibility, or EPR, if you're not familiar with that term. And that leads to more strict reporting requirements and therefore economic incentives around the recoverability of packaging. The consumer part of it, if anytime you've walked down a city street in a big European city, you'll see that there are public containers separated by the major types, your glass, your papers, and your plastics. And so definitely it has driven consumer behavior changes because of the proximity to those different recycling entities. In cases like Germany, there are bottle bills. And so you get paid, and you must get paid for turning in your bottles. And in fact, whoever is producing or delivering you the bottle, like a glass bottle, has the responsibility of collecting it and paying you for it. Fun fact, I used to work at Amazon before Amp Robotics, and we had to actually figure out how drivers could pick up bottles and do that payment all through the app, and that was quite a project for us to work on. So that's just the level of economic policy driving consumer behavior and how consumers are very much in the loop there. Last but not least, and the part that I love talking about, is the technology and the way that you sort. And so because of all those other incentives, economically driving it, there's a large diversion from the landfill. And so there really is all the right technology, be it optical sorters or robots. They both have their place in this industry, and manual sorting to make sure that we are recovering every piece of the commodities available. And it really, really helps that you get clean commodity streams into those facilities, much more so than what we see in the US. But happy to go into more detail. I love talking trash.
Looking
Thanks,
forward.
Amanda.
I guess just to add to that, I guess from a social and economic standpoint, several emerging economies have informal waste sectors where informal waste workers, they pick up trash and they try to make more money and by just selling them and recycling them to the best ability possible. So there's a huge social angle to it as well in the emerging economies.
I guess to continue that question or line of thought, like, is it incorrect that the US also has like these bins that Amanda was talking about separately, that that you could sort your recyclables and the landfill stuff or into? What is kind of the difference that you said in those bins in, say, Germany or somewhere else in the EU?
Yeah, it's kind of unfortunate in the US. It's a dwindling number. It used to be about 50% of locations had a blue bin program or a curbside recycling program where everything was what's called single stream recycling. So it's mixed. You as a consumer do not separate it. It's been going down over the years, just as labor has become a shortage and prices have gone up. It is no longer economically viable for a lot of cities to run their own hauling service, and therefore they no longer offer recycling. You as a consumer can still choose to bring your items to a facility, but most consumers choose not to. We are geographically dispersed, for those of you not located in the US, and so it tends to lead to high driving times. And so for the programs that have curbside recycling, or for the locations that have curbside recycling programs, you do have all those materials coming in and then have to separate them at your material recovery facility or MRF. But many of the locations, like if you think mostly in the southeast of the United States, that's where it's just so geographically dispersed, it's been expensive for those programs to run. So those programs have been canceled. All that same commodity volume, all of your used beverage cans, your UBC or your aluminum cans, those are just going to the landfill. And that's, I can definitely get on my soapbox about how much it hurts my heart that we have all these like raw earth metals going into landfill. And so, certainly want to keep that from happening.
Okay, great. Thanks for answering that.
Just to add the Canadian perspective to this, I'm from Canada originally, and in Canada they don't have this single stream recycling where you put everything, all your recycling into one bin and mix everything together, paper, plastic, metal, and so on. But instead, you have to separate it as a consumer. So if you want the city to take your recycling, you need to give it all separated into material type. So I think it's just that the regulation of this in the US is pretty different from other countries.
Absolutely true. I also recently learned that in Canada, you get your milk in bags instead of in jugs. So it's kind of fun to see the difference in recycling streams in different locations.
I have a question for the organizers. Did you use anybody use the simulator for the recycling trash and succeeded to achieve good performance? You have any better simulators? Because in the autonomous vehicle simulators, it seems to work much better.
Thank you. That's a great question. So we're definitely going to improve the simulation quality of our data. Maybe we will release a new version of data at some point. We believe that the biggest advantage of the synthetic data, for example, for the autonomous driving, comes from the fact that in the autonomous driving, the task is very, very different. There is a very fixed and very strong prior, spatial prior in this domain. For example, we always know that the sky is going to be on top, the building is going to be on somewhere on the right and on the left, and there's going to be a road somewhere like in the center part of the scene. So when you use the synthetic data for tasks like this, what you basically teach your model is those spatial priors about the domain. In our task, because there is no fixed prior on the composition of the scene, objects can appear in arbitrary places and the stream, the use of this synthetic data might have been more limited. But I agree with you. There's definitely some room for improvement in terms of our data. Thank you.
Thanks for that question and for answering, Dina. So we're right up to catching up to our schedule. So let's move on with our invited talks. So first, let me invite Subhranshu for his presentation. Subhranshu is an associate professor at the University of Massachusetts at Amherst, where he's the co-director of the Computer Vision Lab. His research focuses on computer vision with a particular emphasis on algorithms for high-level recognition in order to enable cheap and robust sensing of the visual world. And yeah, with that, I'll hand it over to Subhranshu.
Thank you so much. First, can you all see my screen?
Yes.
And great, and hear me all right?
Yes.
Okay, great. So thank you for having me. It's a pleasure to be here. I was thinking about recycling right before. So I used to live in Netherlands last year and took great pride in recycling all the things. And in Amherst, where I live, there are 6 different types of recycling, which is more than what I can parse. But today, let me just talk about some of the work I've been doing on computer vision for ecology. So about 6 years ago, we started to work on this project on tracking bird migration through weather radars. And I'll tell you a little bit about how cool weather radars are and what they reveal, and also tell you a little bit about 2 domain adaptation challenges that we had to deal with when trying to solve these problems. So a little bit about context of why weather radar. So we want to study bird migration, and birds migrate a lot. So billions of birds are migrating over the US every year. And they, in the summer, come from the south, go up to the north. And a lot of this bird migration happens at night. Birds take off and fly at night, helps them conserve energy. So most of the migration is not visible to us. But the US system has a large network of weather radars, and these weather radars are able to track bird migration. So here's a little video. So each of these white dots is a weather radar station, and we're looking at weather data for the month of April in spring 2018. So each day is about 1.5 seconds, and what you're seeing here are these storm systems going from the east to west. These are big swirls. But you're also seeing these pulses. There's another one. There's another one. So these correspond to nocturnal bird migration. So birds are taking off right around sunset, and they travel north in the spring. And this is happening throughout the US. So you can see as we get to late April, the migration intensity is getting stronger and stronger. And due to the radar geometry, these birds are more easily detected when they're close to the radar center. So you see this ring pattern around it. Okay, so in the US, these weather radars have been operational since the early 90s. Every 6 minutes, each of these radar scans are collected, and this data has been archived for more than 20 years now. So one of the goals for the dark ecology project is to use computer vision, broadly AI, to unlock biological information in this 20-year worth of archive. And this has been a large interdisciplinary collaboration with many people, several others from UMass, also from the Cornell Lab of Ornithology. The goal here is to recover this information, do basic science, and also, since this is such a long spatiotemporal data out there, we can try to make sense of, are there impacts to bird migration relative to climate change and other things. The challenge, of course, it's a very large data set. So thinking about hundreds of millions of scans, and it's very hard for humans to manually go around and remove the info, gather this information. So what is the big challenge here? But before we get there, a little bit about radar. So radars they spin around and they collect reflectivity information and a few other things. So what you're seeing here is a radar at an angle half a degree. It scans the atmosphere by spinning around, and based on the reflectivity you get back, you measure whatever is in the volume at that angle. What you're used to seeing in weather reports every day are these top-down views, and they correspond to some elevation in the radar scan. And the radars typically scan the volume at multiple angles. So that takes about 6 minutes, and then it restarts again, and you get this volumetric scan. So the important thing to remember is, because it's an angle, things closer to the center at a lower elevation, and bird migration happens at lower elevations compared to, let's say, rain. So things are easily detected closer to the center. That's why those pulses were brighter at the center of the radar. So the big problem in weather radars is they detect weather. So here you're looking at a scan where you see these blob-like things. This is rain, and then the other more diffuse pattern that's at the center is biology. So that tends to be more uniform and more widespread compared to this. And as humans, we can see these patterns and remove the rain. But if you're trying to track biology, this is a big problem. If you're measuring reflectivity without removing the rain, rain tends to be orders of magnitude more stronger. So it dominates biology. But if you're doing weather modeling, biology isn't a problem. So we would like to screen rain, and that's one of the big challenges to doing this large-scale study. So at the time of when we started this work, most US studies were done with manual screening. So you'd go through scans, remove ones with rain. That doesn't scale very well. There are some machine learning algorithms that existed. So for example, the radars have been in operation for a long time, and the sensor has been changing. So one of the big changes was this dual polarization upgrade. I'll talk about that in a little bit. And that made rain detection a lot easier. So post 2013, there are simple algorithms to remove rain. And then there were techniques based on machine learning, looking at vertical profiles of reflectivity across scans, because rain tends to exist across multiple heights. There were techniques that could remove the scan. The problem, of course, was these techniques were discarding a lot of biomass that coexisted with precipitation, and but even then, just being able to do machine learning at scale let people analyze a very large collection of data for the first time. So we built this connet called MistNet. It takes these radar scans and some other things it collects. So the left one was the reflectivity that I mentioned, but it also collects radial velocity based on Doppler effects and some other things. So it takes these inputs and predicts background biology and precipitation. This is a standard convolutional, a fully convolutional network. And the big challenge was, how do we train it? And for this, this is where the dual polarization upgrade became a useful source of labels. So after the dual polarization upgrade, what the radar does, it collects reflectivity across two different orientations. So it looks at horizontally polarized scan beam and a vertical one. And looking at the ratio of these two gives you some sense of the aspect ratio of the targets. So to a rough approximation, rain is round, birds are flatter, and just that signal is enough to tell apart biology from rain. What that let us do is we now have a large amount of noisy label data, and we could train a ConNet that could take the legacy data and try to predict the labels obtained from the upgraded data. And we could synthetically go back in history. We could synthesize all forms of legacy data, including low resolution data, which was around 2008 prior to that, and basically have synthetic data, synthetically labeled data in very large numbers. Yes, so sometimes your sensor just gets better, that the problem becomes trivial, and you can distill this simple model from this more recent sensor and train a more complex ConNet in this case to label the data. And that worked really well. And we trained a model that could remove rain from biology. And here's an output like this. And on some of the evaluation metrics we looked at, the MISNet was just as good as dual pol, but could work with the legacy data. So it kept about 98.7 of what we thought is biology, and only got rid of that was the precision, and the recall was about 96%. So that just allowed us to go back in history and process all of the data. And this is a snapshot of how bird migration looks like on average. So processing about 13 million scans, about a year of compute time, you can start to build this big, large-scale scans of what nocturnal bird migration looks like. And the data is very detailed. So for example, you can look at Houston and in 2018 and look at what's the migration traffic rate at that location. And you see these sorts of special days where the conditions are just right, that for example, the night of April 29th accounts for 10% of all the bird migration. Here's a video of the migration flow on average. So this is all the years from 1995 to 2019, about 30 million scans. And what you're seeing here, I don't know if the Zoom is able to show these videos correctly, but if you're seeing this, you see this in the spring, there's a big flow of birds coming from the south, and they go up north to feed and to breed. So now you'll start seeing a little bit of flow going north. And then again, they'll head back in the fall. And the fall migration is more concentrated around the East Coast. Okay. So this is quite nice because
can I ask quickly?
Yes.
Just stands out to me that it's all on the East Coast. Is that just
Yeah, so the middle here are the Rockies. So we don't have a good radar, and there's also not much activity there. So you have stuff on the West Coast. You see a band there, but a lot more along the East Coast, where first there are a lot more radars there. So some of we don't quite know what's happening in those mountain ranges, but there are also mountain ranges. So there's probably less things there blocking off geographically. Okay, and what I was going to say earlier is compared to things like eBird, which is often user-collected data, nothing else spans that large spatiotemporal range and has such detailed coverage, unlike radar. And then because you're looking at 2 decades worth of data, you could start to look at phenology at the super long temporal scale. And one of the studies we did from this data showed that spring migration is shifting earlier by about 1.5 days per decade. And this is correlated with changes in temperature in this part of the world. Okay. Another fun project we've been looking at is tracking roosting birds. So there are a lot of species of birds that gather together in flocks, like tree swallows or even bats, for example. And they're large enough that as they fly together or leave their nocturnal roosting locations, they show up on radar. So we've been building object detection models to track these roosts in weather radars. So this is also another collaboration with various people in Colorado State University and University of Oklahoma. And just to show you what these roosts look like, so this is a swallow roost leaving their roosting location. It was like a sugarcane field, and right before sunrise, they often leave together in big flocks. So some of these could contain 100,000, even 1 million birds in them. And as a biologist, these are interesting species because these are aerial insectivores. So they fly in the morning and snack in the air, eating insects. And insects are in decline. So knowing a little bit about their phenology of these birds and their population decline might give us a sense of these other species as well. And so swallows, for example, if you look at radar scans of them in the morning, these big growing blobs are one of these roosts. So they're quite evident. If you know where to look for, you can see them all the time. But here's one of the scans, for example, showing around sunrise time. These are multiple scans around 6 minutes apart. See these ring patterns. Okay, so it's relatively easy to train an object detector. So you could take these scans, you label bounding boxes, and collect the data. And you can train a faster CNN to be a little bit careful on how do you deal with this volumetric rendering and what inputs to take. And you can build an object detector and tracker out of it. One of the challenges we faced is often if you're collecting biological data, you have annotators who opportunistically label data to do various scientific studies. And they often lack a protocol how to label. So you end up with data with different annotation styles. So for example, in this data set, you had one annotator go label these roosts, and he decided to draw roosts that are quite tight bounding boxes. So you have this ground truth green box at the top row being inside the roost area, whereas the second annotator decided to label things that is a bit more diffuse. And this is often what happens when you're doing a sort of trying to understand a phenomena that you don't understand ahead of time. You label, and then you sort of define the protocol of labeling as you go along. And that causes changes in annotation styles, which leads to training being very brittle. So for example, we trained an object detector for this kind of phenomena and found that the performance is not very good. And it turns out that's because the way we evaluate object detectors based on overlap tend to consider these detections at top as false positives. But this is not really a false positive because there's this latent annotation style that varies from case study to data sets to annotators, and training it in the standard way leads to evaluation bias and so on. So in one of these papers led by my student, we built a latent variable model where we said that each of these data sets or annotators has a unique labeling styles. And as part of training, we would learn these user-specific style biases. In this case, relative scaling and translation factors. And we can then train the detector by correcting these bounding boxes. So this idea is quite general, and you can apply that to many settings where you're collecting labeled data sets from multiple sources, and you don't, or you can't rule out labeling biases that are data set specific. And you can learn these biases together with the model that you're trying to learn, helps you get a little bit. So for example, if you train and test across different stations that were labeled by different users, the standard RCNN model, the fourth column, has big variability across stations. But once you correct for these labeling biases, you get a much more robust sense of performance, and also a better detector. Okay, this is another adaptation challenge that often arises when you're collecting crowdsourced or community data from many years of data sets. So here's an example of some of the roosts it detects. So we deployed this roost data across many years of the radar data, and you can start to build maps of species level migration. So radar doesn't give you species level information. The MISNet, for example, is just all biology, but because in roosts or tree swallows are one of the only species that roost in this time of the year in the US, you can start to build maps for species and where do they live, what kinds of wetlands or agricultural fields do they depend on. And this could inform things like when should you harvest, or what impact does harvesting times have on other things, and so on. And then recently we deployed this detector on all of 21 years of data from the Great Lakes region. So this is the set of radar stations around the Great Lakes in the US, so Lake Michigan and a bunch of areas. And there are lots of swallow roosts there. And one of the things you can do is start to collect this data and build maps of when does roosting activity happen across years. That's shown on the top right. And then also trends in this phenology. So peak roosting phenology is advancing by 2.5 days per decade. So this is similar to the result on the bird migration as a whole. This is even stronger effect than the previous one. Okay. So let me wrap up here. So thank you very much. Hopefully, I was able to show you a little bit of how radars can reveal broad-scale migration across the US. And then if you start to go beyond US, different countries have different radars. So Canada has a different type of radar, and they also collect archive data. So that's another adaptation challenge. And then sensors vary across time. So the sensors are constantly being adapted and changed. So you have to worry about the sensor variability, but that's also an opportunity because the newer sensors are more accurate, and you can go back and retrain your model and build a better detector for the legacy data. And there's also labeling variability due to labeling biases. And we've built this open source version of all of these models, which you can check out on the Dark Ecology page. And it's a large interdisciplinary project. I talked about a few papers, so go check them out if you want to off my publications page. Thanks.
Great. Thanks for the great talk, Subhranshu. We can maybe take one question. Yeah, I even forgot to send the reminder that I promised in the beginning. If there
I have a quick one.
Yeah.
And I'm talking next, so it'll be a nice auditory transition. Yeah, perfect. Really cool body of work here. And I'm curious if you're at all involved in the NEON project or those data sets.
Yeah, so the one with the roost one is closely tied to NEON because we wanted to look at phenology of insects. So Elska, who is on the team, she's been looking at NEON data. But NEON data is very sparse. So NEON, if people don't know, it's a collection of it's a network of sensors that collect temperature, insect activity, a whole bunch of things, but they tend to be sparse a few times a year, and often there are biases because where you place them matters and so on. So it's turning out the data there. It's hard to interpret, and I certainly don't have the knowledge myself to make sense of it, but we're trying to correlate because these are swallows and others, and so aerial insectivores, you would think that the places they roost and other things might be correlated with insect activity and populations and so on.
Yeah, it certainly sounds interrelated. Cool. I might follow up with you about that later. It's some really great work. So much, Faye.
Thanks for the question and the presentation. And next up is Colorado. Let me quickly say Colorado is a final year computer science PhD candidate at the Berkeley Artificial Intelligence Research Lab and a visiting researcher at Meta AI. His work aims at advancing fundamental AI research by directly addressing scientific problems related to environment and climate change. He's a co-creator and organizer of the Berkeley AI Research Climate Initiative. Please take it away, Colorado. Thanks.
Yeah, thanks for the intro, and thanks for putting this all together. I'll start my own timer as well, just to make sure that I go over. Okay, very cool. So let's start with a little whimsical title: From AI for Science to Science for AI, a tale of ice and fire and domain adaptation. So this is kind of a fun presentation, and I think it's going to be nicely in line with a lot of what we've discussed today, where we really talk about going down and looking at some crucial applications and saying, how do we work backwards to solve these types of problems, rather than saying, let's create some interesting AI and a black box in our labs with some benchmark data sets and then see where we can apply it. Let's go the other direction. So let's jump into that. And there has been a lot in the media posted about AI for science recently, right? So Nature, how AI is helping the natural sciences. The Gradient says AI is ushering in a new scientific revolution, the AI revolution in science, from Science, how artificial intelligence is changing science. These same titles appear again and again, and you'll probably see one again and again in the coming weeks and months in places like the New York Times and the Washington Post and the Economist. It's a really nice story, right? Like, the AI saviors are coming to science. They're going to solve all the problems. And for those of us who are scientists, who have worked with scientists, I don't know if we really like this kind of dialogue, so to speak, or this sort of headline, right? That this AI parachute science is coming to save us all. And I think the other way to really look at this and saying AI for science is actually going the other way and saying, okay, there's so many great and interesting problems in science with deep and rich histories and very smart and very capable researchers and professors. How can we, as a relatively young field, learn from them? How can we address their problems that are of interest, take those back, and mature our field? And that has been part of the philosophy of the Berkeley Climate Initiative that I've helped build. It's been a part of my PhD work, and I would like it to be a part of our community more broadly going forward. I should say there's lots of really great people and organizations that think like this. DeepMind comes to mind immediately. They go and they say, here's some really hard science problems. Let's collaborate with the scientists and figure it out. And so I want to walk through a bit of a detailed example today of one of these types of problems and keep it kind of light and interesting, but point out how this approach and going down into one of these problems really allows for this green field of research to appear, right? Instead of chasing the same benchmarks and data sets as everybody else, when you start really looking at scientific problems, especially, there's so much to be done and a lot of areas for AI to have a role and to have a meaningful role. So let me talk about one of those specifically. And I'll start with one of my co-employers, which is Meta. I work at Meta as a visiting researcher. And Meta, as you may or may not know, has a pretty aggressive water initiative where they are committed to being water positive by 2030, which means they want to restore more water to the environment than all of its global operations consume. And that is primarily from their data centers and their cooling, but it also goes into things as straightforward as people washing their hands at the office, right? And well, okay, what's the water positive strategy? If you ask any hydrologist how to go about such an initiative for a major worldwide employer like Meta, something like 100,000 employees and operations across countries, they say, well, it depends where you get the water. Because if you take a cup of water from the desert and you put a cup of water back in the rainforest, like that's not a particularly good trade-off. So it's really important to actually take into account where you're getting the water. And so when you start to unravel that thread just a little bit, you end up talking about snowmelt. And as it turns out, snowmelt is this critical water supply for about 1/7 of the world's population, about 1.2 billion people. And this is just a heat map showing where it's particularly important. And in the Northern Hemisphere, it's particularly important, some places in South America, but critically, it's important at Meta HQ, right? Meta HQ is in Menlo Park, California. California, though we don't think of it as a desert, by all means and all measures is. It is a water scarce region in which we are fully snowmelt dependent throughout the summer and fall months. So quick snowmelt 101. On the right, I have a California water system, arguably the most complex and politically charged water system in the entire world. And each of these dots shows different reservoirs. Some of them are privately owned, which I still honestly don't really understand, and it seems kind of like a direct conflict of interest. But okay, forgetting about that for a second, each of these shows different reservoirs, different colors, and they're interconnected through canals and aqueducts and all sorts of different channels. And what happens is in the wintertime, it snows up in the mountains. And for most of mid and northern California, that's the Sierra Nevadas. And for Southern California, it gets actually a lot of water from the Colorado River. So that comes from the Rockies. And then in the springtime, politicians and hydrologists and water resource managers get together and they do water allocation for all of these communities, right? In which they set their reservoir flow rates. And this is critical because if you have one particular reservoir and some channels connecting to another reservoir, the flow rate at the feeding reservoir is going to largely determine how much water will go into other reservoirs, other communities along the way, other agricultural providers along the way. And it's going to determine how much water stays at that reservoir. So it's all a very interconnected system with a lot of money at play. There's about $50 billion in agricultural commodities at play every season in California, right? We grow a lot, which means we use a lot of water. So we do this allocation, and in the summer and the fall, the snowmelt provides water. So there's no rain during this period. If you've lived in this area, you're well aware of that. Okay, so where's AI come in? Where does hydrology come in? It comes on number 2, which is this water allocation. Because as it turns out, if you misallocate and you can't do accurate allocations to set these reservoir flow rates, then you waste water, right? You either keep water at reservoirs that could be fed to communities, or it goes through the entire system and basically feeds one way or another into the ocean. And there's various measurements, and this depends on the year, but to give you an order of magnitude estimate, this misallocation can result in billions of gallons of water lost every day. And to give you an idea of magnitude we're talking about with Facebook's water initiative, they're looking to replace about 1 billion gallons of water per year. So at least 2, or higher orders of magnitude difference kind of in those interplay just in California. Talk to hydrologists, snowmelt forecasting, a lot of money, a lot of interest, but it's a long-standing problem. To give you a sense of this problem, the April to July forecasts in the American River Basin here in the Sierra Nevadas, which is arguably the most well-instrumented, well-researched, well-funded basin in the entire world, has a median error of about 20%. And a 90th percentile error, so 1 year out of every 10, over 60%. And those 1 year out of every 10 are really problematic because effectively what happens is we're just completely wrong. And I talk to hydrologists and they kind of chuckle every water season and they think, well, is this going to be the year? Where we do things like what happened in August of 2021, where we have to shut down an entire hydroelectric plant because our reservoir water level drops too low. Right? So yes, 20% error is bad, but when you start actually completely misestimating and misallocating water, then power plants that can power 500,000 to 1 million homes fully shut down. And it's going to get worse with climate change. So I ask a hydrologist. This is somebody I collaborate with, Dr. Daniel Feldman, hydrologist at Berkeley National Lab. I say, why is this so difficult? And he says, our in situ point estimates of snowpack provide a limited view of the actual snowpack coverage, and our physical models then assimilate this data. So we have these things called snow pillows or snow tells spread all throughout the US and Canada and Alaska, and they provide point estimates of how much snow we have. And that's what a lot of our physical models fully build on. But they're very sparse, and they tend to be at places where humans can access them. So they tend to be at lower altitudes and elevations, right? More accessible, but later in the snow year, later in the summer and fall, there's more snow at the higher points because it stays colder and the trade-offs with pressure and so on. And Daniel says, but it's really hard to figure out how to bring in new sources of data. Think 1 PhD per data source. It's one data source, one location. That's a new doctor, right? Berkeley created a new doctor. Now we've assimilated one new data source, and how long is that going to be relevant, sort of thing. So in other words, it's done. There's a lot of money and interest at play, but it's very hard. So we're looking for better ways. He says, if we can better incorporate more data sources, and he's looking at AI for this, then we can obtain more robust snowmelt forecasts, which can result in saving a lot of water through this allocation strategy. So we went out and collected, just in California alone, all the relevant data sources. I don't expect you to read these, but just to give you a sense, these are 36 different remote sensing data sources. I think we now have something like 60 remote sensing data sources that can be relevant. A lot of data. And as a shorthand, we call these data sources OMS, right? Observational, multimodal, multi-scale, spatiotemporal. And you can think OMS like ohms if you've had a yoga class recently. And OMS data, if you've worked, and ecologists certainly know this, but hydrologists do as well, they work across different scales. So, in hydrology, we have a basin scale or a watershed scale, and you can see this little rectangle here that's showing the kind of the relationship, and then this little rectangle here all the way down to the reaction scale. And each of these provide a complementary piece to the puzzle of answering something like, how much snow do we have and how much water can we then use, right? So across all of this different observational data, it operates at different scales with different measurement devices, and is collected at different spatiotemporal frequencies. Okay, no wonder this is so hard. No wonder there's PhDs for each time we want to incorporate a new data source. And this is exactly some data I put out in the temporal range to show you. These are something like 16 different data sources we were using for one challenge around predicting snowpack. You can see there's different temporal coverages here in the optical and the different microwave modalities and gravitational. And there's all sorts of different remote sensing things that matter, all with different periods of time that they measured. So domain adaptation experts and aspiring experts in the audience, this is the type of thing where you look at it and you say, you know what, that's a hard problem. These are all individual, it can be treated as individual domains with different relationships that are all measuring one aspect of, say, snowpack, right? They're all feeling one different part of the elephant if we go back to that analogy. So to make it concrete input, we have these OMS data sources across different modalities and spatiotemporal coverages and scales. And the output, we want something like a dense snowpack estimate. A dense snowpack estimate that could both itself be used to understand how much snow we have, or fed into physical models, right? It's not necessarily either or, fed into physical models to provide additional information that can be incorporated. And this could be something like, these types of dense snowpack estimates can be a form of modularity where you have the one PhD student doing the data assimilation into the physical model, and then you have a community of AI researchers figuring out how to give that right type of input. I like to ask folks, you get 20 different data scientists or AI experts, and you say, well, how would you solve this problem? And you probably get around 19 different answers, the birthday paradox saying that you'll get at least one overlap sort of thing. But okay, it sort of looks like this. Step one, you have to acquire the data. You're working with 20 different data sources, 40 or 60 different data sources. That itself is going to be quite a challenge. Step two is you explore various AI methodologies. This depends on the audience that you have, right? Your expertise, what you've worked on before, but there's some really interesting commonalities that result. So from the observational side, you're dealing with a lot of missing data and a lot of uncertainties associated with the different data that you measure, right? There's no such thing as like, this is the pixel value. It's something like, well, we think this is the pixel value and here's an error range. So we deal with uncertainty quantification. Multimodal, this is really where I see a lot of potential for things like domain adaptation, different strategies. Multi-scale, one thing that's been fun here is working with the physics community to explicitly model the interactions and the scales that are at play here. We know the scales we're working with, and I'll briefly touch on some methodology there in a second, and so we can inform from those. And then the spatiotemporal aspect just makes everything harder. And then number 3 is looking at the scientific results, and that's where folks like us in the AI community have to form deep collaborations with the scientists to say, how can we actually make this meaningful? Because a lot of times, just having a prediction, just winning a competition, kudos to the winners, but right, that's not the end of the road. We want to see that actually transition into meaningful science and meaningful results out among us. And of course, each of these 3 steps is significantly more effort than a standard AI problem, right? And that's why I think as a community, we tend to shy away from this. And in industry, we have no other choice than to actually make things work. So they tend to do this. And in the other sciences, they don't want to just stop at the methodology. But it's an effort worth finding because there are so many interesting problems and lots of green fields here. So these 3 steps I call the 3-headed hydra. More specifically, I call it the DALL-E 2 generated 3-headed hydra, which I now own. Thank you, Dolly. So let me talk about these 3 steps and some different things we've done here. The first one is acquiring the data. This is a total pain if you try to work with massive amounts of remote sensing data. So we started to develop and build a library we call Multi-Earth, where the idea is you can feed in a single unified configuration that's going to specify the different satellites, the different ranges, the different bands, the different types of data you want. Multi-Earth will then go pull it from all the different possible remote sensing providers, both public and private, and extract it into a usable data format for machine learning, right? And so this is just a practical thing of working with lots of different data on lots of different systems. I work with Meta, I work with Berkeley, so going back and forth between a lot of those, this has made my life a lot easier after, of course, developing a library. There's a GitHub link here, or if you just Google, Multi-Earth or so on, you should find it. There's excellent room for methodology here. So we just submitted a paper to a computer vision conference that I don't know if I'm supposed to name, but you can probably figure it out, called Scale MAE. This is a masked autoencoder, where what we were doing was a scale-aware masked autoencoder for multi-scale geospatial representation learning. Saying that we have all of this different data at different scales, how can we learn representations that directly leverage and condition on the different scales of your data? The way this works, and I've kind of blocked it out because I don't want to get into too many details for this quick overview, is that you input an image at a certain known scale or ground sample distance, GSD, and then you're going to mask it, and you're going to use an autoencoder to reconstruct it at higher and lower known resolutions, and you're going to do that at higher or lower frequencies. So there's lots of tricks. Feel free to let me know if you want to see this. It should be on archive here in a week or 2. And there was lots of tricks to get this to work, but they're not too important. And I'll skip over this one kind of interesting part, which was actually how we managed to sort of change the positional encodings so that they take into account the actual scale that you're working with, as opposed to the traditional ones that are the same for every image. It's a cool little detail, but I have about 2 minutes left, so let me jump through. There's fun visualizations. Oh, okay, but critically, I should point out, our method here is the orange method, and the other state of the art is the blue one. So across all of these things, we're clearly doing better. But there's a lot, in all seriousness, there's lots of really interesting results where you take different data sets at different scales and show that using this method of pre-training leads to better representations. And so you end up with some really nice gaps, better performance across the board. A key part, and what I want to finish with here in the next couple of minutes, is that scientific head of the Hydra. Right, we talked about some of the tools to getting the data, to doing some methodology with it. How do we actually make it important? And one thing that has to be justified to the hydrologic community is that AI is necessary. To some, they might say necessary evil. I think it can be a necessary benefit. where I mentioned that there's all sorts of snow tells, these snow measurement devices throughout the US and in Canada and Alaska. You can see they look pretty dense here on the left, all these blue points. But if you zoom in, and each one of these pixels here is 9 kilometers squared. And this one spot, which is about a 3 meter by 3 meter sensor pillow, is with a star. And so this one snow tell here, station, has to actually cover about 200 square kilometers, this whole region. This is a basin that we care about, right? And these values are actually something we've determined, which is how correlated the snow tell measurement is with these 9 kilometer by 9 kilometer little square pixels here. You can see, judging by these values, they're all pretty low. And in fact, not only are they low, this is using reanalysis data, historical data here up to 2020. This is how much error they have. You can see it's about 20%, as I had mentioned before. It's all related. But as climate change comes about and things start getting warmer and the snow starts moving higher and higher up, they get even less correlated and our errors go through the roof and we end up with all sorts of variability here. And the idea that we bring to the hydrologic community is that we are using all of the sensors that we have, and we need to work towards more robust and multimodal measurements that can be relied on in a changing climate. So we need to explore all options to do that. And that's really the role AI has to play. So just like I said, build more robust and resilient snowpack estimates by incorporating more OMS data. And each of these data sources has its own properties and distributions and availability. And there are many open problems in domain adaptation here. So if this sounds interesting at all, feel free to reach out. I'm happy to take any questions or chat offline. Thanks, guys.
Thanks, Colorado. Great talk. Let's again just do one question. That's kind of what we have time for, if there's one.
Hi, Colorado. I have one question.
Sure
Great
thing.
talk. Yeah. I think I'm digging through my memory, and I remember planning ski trips using CalTopo, and they have a snow thickness layer basically in CalTopo, and yeah, I've just used that to sort of map out depth in the springtime, especially when it's not clear at where the snow line is. I'm curious if that data is just really garbage. Like, is it just not good enough for like basically integrating and computing the amount of water, or what's going on there?
Yeah, great question. And for skiing, these snow trips, right? Seeing where we have snow coverage from satellite data is really easy. That's basically a solved problem, right? So we know where we have snow, and then we have some measurements that give us some rough idea of depth. And what you're using is probably some physical models that have extrapolated from there. And if they're off by 20%, you're right, and not 20% in terms of coverage, 20% in terms of something like depth, right? So instead of being 10 inches thick, it's 8. Right? That's not going to really impact your ski trip that much. Like, you're probably still going to have a good time, I hope. But that 20%, or if it's 4 inches instead of 10 inches, can be a huge difference in terms of the amount of volume of water you're going to have from the runoff. And so those tools are great for that application. But when it comes down to actually trying to say how many gallons of water can we give to this farm or to this community or to this power plant, 10, 20, 40% differences can make a huge impact.
Yep, makes sense. And then just a very quick follow-up. Are there problems in terms of snow density? I know snow can fall as very light snow and snow can fall as very dense snow. And then, so then it can literally be like 3 times the depth with the same amount of water.
Yes, that is, we work with something called snow water equivalent, which is designed to take that into account. There's all sorts of physical models. They call them layer models, which is like every time you have a snowfall, right, it creates a new layer, and then that's going to be impacted by the wind and the sublimation that happens, and if it rains on top of that, or if it snows some more. And so you kind of try to analyze the physical ways to do it layer by layer for each new snowfall. And so it's kind of changed. It's not homogeneous throughout either. It changes at different layers. But yeah, it's a very hard, long-standing problem for these reasons, and different satellites and different radars and things have different reflectance properties depending on the types of layers. And so you can kind of model those and then see how they actually impact the data you get. And it's a work in progress.
Very cool. Thank you.
Great questions. Yeah, thanks, Peter.
Yeah, thanks for the question. And yeah, thanks again for the talk, Colorado. Next, let me invite Amanda Mars. Amanda is a Senior Director of Product for AMP Robotics, responsible for technical product development for the company's AI platform, robotic sorting systems, and software capabilities. She has more than 10 years of experience in product development at GE and Amazon, with a focus on hardware and software products used in industrial processes. Take it away, Amanda.
Yeah, thanks so much. So happy to be here and so impressed by all these presentations and the different projects. I feel like I learned a lot about birds and about water today. So now for trash. Yeah, as I mentioned a little bit before, AMP is really focused on how do we use AI and robotics, or really multitude of sortation options to reduce the waste that is going to landfills. Specifically, the problem statement is billions of dollars a year of commodities are in the landfill. It's just not cost effective to go after it. Maybe like we talked about a little bit earlier, there aren't curbside recycling programs and there's no great way to recover these materials, but they are inherently valuable materials. They are commodities. And so that is our big problem statement that we're focused on, is how do we keep all of those commodities that are going to landfill, how do we keep that from happening? And so our tagline is, we envision a world without waste. It's a really lofty tagline, but it's one of those North Star visions that we then can work backwards from and say, okay, everything that gets into landfill, how do we start to just, chip away at the big, hairy problem? Our approach to it is to use technology. And so we have the technology that we will bundle up into nice little packages and sell it to the material recovery facilities, or MRFs, where they do the sortation. But we more recently last year announced that we have 3 facilities that we've built and designed to the complete facility to take materials that were either undesirable in the way that they were sorted, or it was residue lines about to go to the landfill. And we're mining all of that to sort it into more valuable commodities to put back into the market. So one of the things I personally love about this industry is it's not just the feel good of, the sustainability, the world impact, but it is a circular economy, and it is a part of the global supply chain, and how we've become all more aware of the constraints on the global supply chain over the last couple of years. This is one of those ways that helps. So just a little bit about AMP Robotics. I think it's important, as we're talking about the technology, to also have a little understanding of the history it took for that technology to get out to the place where it is today. So AMP started way back in 2014. It's hard to imagine that it's 2022. It feels like we're still, at the beginning of this journey. Our founder and CEO, Matanya Horowitz, has multiple degrees. Very fun to take a look at his background and at all the things he worked on. But robotics and AI were certainly in there. And so when he was going through his PhD program, I heard you say a little bit earlier about, building an AI model in a lab and then applying it to the real world. Well, back in 2014, that was a little bit of what was happening. It was still a very new field, and we were looking for all the opportunities where this could help solve, a big, hairy problem. Something that really wasn't cost effective and something that did have a big scale. And so that's a little bit of our origin story. But here we are now in a fully global solution. And just for a couple of numbers around that, over 300 systems employed across the world. And so on an annual basis, this number is already outdated, 50 billion objects detected. It just keeps going up with every installation we get. And so it's really, really cool from, the humble origin story of a little bit academic, a little bit new, with the technology, and then figuring out how to bring it to the world to, holy cow, there's such a, big opportunity here. Fun fact, an EPA study from 2019 said that in the US, we generate about 5 pounds of waste per person per day. 5 pounds of waste per person per day. If I knew my metric system better, I would translate that into a metric number. But it's a lot. It's a lot, and it's an embarrassing amount. And so that is something that just keeps getting bigger and bigger. Population increases, and the use of this packaging increases. Just for context, in the 1970s, that number was about 2.4 pounds, so almost a doubling in about 40 years. So that's where we are as far as, our footprint to go tackle that big, hairy problem. Very quick overview, not super technical overview of our systems that we put in place at these facilities. It starts with our vision system, and we are pure RGB vision system. There's so much, as you're aware here, that you can do with RGB. We always like to tell our customers, if you can train a human to see it, we can train the AI to see it. And in many cases, the AI can see it better and faster than a human can, especially on these moving belts. These belts can go 100 to 400 feet per minute. Again, I need to work on my metric conversions, but that's pretty fast. A human gets very dizzy in those situations. And then it's just, it's too much material on the belt. So it's just really hard to make that inference really quickly. So that's part of where, the vision system is bringing a lot to this this industry, and it's also now capturing a lot of data that before there was no data. So you couldn't do material composition analyses on what was on the belt. You didn't have this data to go back and look at seasonal trends or to make investment decisions on what other sortation points should you put in your facility. So really, really cool that we are now able to, capture the data and interpret it and call out all these great stats from it. So we then, say, okay, based on the customer's pick settings, what they're doing, let's drive a pick command to a robot. And so we have, a bunch of software optimization there to say what to go pick, how to go pick it, how do we make sure we have the best cycle time, how do we make sure we have the best grip success? Because it's not enough to attempt to grip the object. In the real world, it matters that we actually grip the object and we get it into the right bunker. And we use Delta style robots. We love a lot about them. And so we've really made that a core part of our different portfolio of robots. They're just very maintainable, very sturdy. One of the nice things about recycling as an application for robotics, for any of you who like looking at robots in different applications, we don't have to keep the product that we're going to pick really intact. If you're picking tomatoes, or if you're picking something that's softer, you have to be gentle with it. But with recycling, it's already kind of dirty and kind of mushed up, so we get to just slam down on it, make sure we get a nice tight air seal, pick it up, and then move it over to the bunker where we throw it in. So it's a pretty easy application for robotics. The hardest part is that it's a very dirty environment. Last but not least, all that data I mentioned, we have a way to show it to customers, drive alerts, drive reports, and ultimately roll up all those numbers into things like extended producer responsibility reports and use that to really influence policy and decision making. But we're here to talk about AI today. So a little bit about the types of materials that we look at. Depending on where a facility is located really depends on what they want to be able to see, and therefore what they want to be able to sort. And so generically, we classify our different materials into these high level categories of the type of material. But we also use subheads in our AI to train out things like, well, not only is it a bottle, but does it have a wrapped label on it? Is it, what color is it? Because that can make a difference in how to recycle things. Does it have a cap still on it or not, right? And these are, is it food grade? That's a big one in the industry right now as well. And so these are all different ways that you start to get this combinatorial effect on how many labels do you have? Well, we could probably count over 1,000 if we really did all of that. But pretty cool to get to see, all the different presentation of material and how to roll it up. And so, key message here is we've been working on this since 2014. We're at scale today. The adoption over the last few years, especially with labor shortages, has really just made this widely adopted in the industry. So no more are we trying to prove AI works. No more are we trying to prove that robots have a return on investment. It's a really great adoption from the industry to put technology in. And so what I want to talk about a little bit more is the AI specifically. And so because we have this large installed base, we're continually getting these images that we'll train our data set on. And so this is where we can go back and look at 50 billion objects annually and start to split out. Okay, now let's figure out what has wrapped. Now let's figure out what has caps and start to grow the neural network from there. We also get customer specific requests sometimes for kind of funny things. For any of you located in the UK, there's something called a Yazoo bottle, which is kind of this yellow plastic container. That's one that we recently trained for a customer because they wanted to be able to pull that specifically from a stream. So it's kind of fun that we can go very broad with class, we can go very specific with objects. And of course, using AI and pattern recognition, we can also train for labels, for brand labels, I mean. So for example, we have a label that is Starbucks cups, because that Starbucks logo with that green mermaid logo is very specific and very identifiable. What else? And just the power of the whole network and how broad you get. And just in a way, it kind of slows you down, but it also speeds you up, as I'm sure you're all aware of. So I want to go a little bit briefly, I'll get us back on time here, but a little bit briefly on some of the challenges that we came across in that journey from 2014 to now. And it's really not any different than what I've heard you all present on in the other projects. But just, in the history of AMP, really when we were starting out in 2014, 2015, it really was how do we get data and having to build out a data set that immediately we were hit with how much variety was in a material stream. And so we were focusing on one specific facility at a time rather than generalizing a neural network. We were doing, one instance at a time. As we started to get more installations and start to see, where we've trained things out to a maturity, and then you start to generalize, that was going great, but, much, much more as we're at 250 installations plus. And so now it's really about how do we continue development speed, accuracy improvements, and introducing new labels without bringing everything else down. So I heard at the beginning one of the presentations about the load on the edge, and that's definitely something we have to keep in mind. Our assets are installed, deployed out at the edge, and then we'll push over their neural net updates, but we have to make sure that we're not overloading what we have there, and making sure that it's happening really fast. We want to make sure that that latency between the inference at the edge and driving the robot fits within the belt speed and the distance that we have on the belt. So all of it starts to become really connected as a system. What other challenges? Deformation. So one of the great things is that everything is crumpled and messed up and we can punch down on it. But one of the hard things is everything's crumpled and messed up and dirty. And so just, the amount of objects that you need when things aren't showing up in a really nice way, it just increases so that you get all the variety of it. So that's what we look at on the right all day, folks. It's just images of waste. Another thing is that it's across everything. And so you start to get some high confusion of objects that when they're in that crumpled state really can visually look like each other. Fiber, and if you look at like this middle picture, it's kind of a shiny fiber that also looks like a shiny plastic. And so it starts to get really interesting how you have to identify certain things like how something is ripped on an edge, or a certain degree of the shine to make a difference. And one of the great things I mentioned about being able to train to a brand label or an image, is wonderful, except if those things are repeated in slightly different ways. So we use the example here of the cow on the Horizon milk bottle versus, the other plastic milk bottle that has a cow on it. And so it starts to become, you almost need more specificity to be able to say, no, this logo is not just generic cow, it's a Horizons cow versus a generic cow. And so that's been some of the fun we've had to train. We really do dumpster dive all day long and look for different examples. It's super fun. But ultimately what we've done is we've created this neural network with thousands of potential labels when you do all the combinations, and these different plastics, which tend to be the most things that you need to separate into specific categories. Just getting it in a way that we can build blends of bales or the specific bales that customers want. And just for those of you who don't get to look at these pictures all day, this is really the main verticals we look in, and these are how these commodity bales get put together with plastics, papers, metals. We also work in the industrial verticals for construction demolition and electronic scrap and organics. Mostly with organics, it's pulling out your paper and your plastic contamination or your metal contamination from an organic stream. So I figured I would stop there and we can take some questions.
Great,
I
thanks
have
for
a
the talk.
question.
Go ahead.
Thank you, Amanda. That was a great presentation. I just wanted to ask, is there any limitation on where the AMP robots can be deployed nowadays? Is it more towards the beginning of the lines, or is it at the final stages of sorting?
Yeah.
Talk about it.
Yeah, that's a great question. So the beginning of the lines will have what we call high burden depth, where you just have a lot of materials on top of each other because it hasn't gone through its series of sorts to kind of get spread out yet. And AI is only as good as being able to see the top layer. Really, most sensors are only as good as being able to see the top layer. And certainly when you go to pick something, you're only able to really grab from there. You're not digging through anything to pull it out. And so we prefer to be in locations where either the belt is sped up enough to spread things out, or we typically will be on quality control lines, whether it's for fiber or for plastics, pulling out either contaminants or the desired object, or on residue lines, which is kind of your last chance line right before it goes to landfill. And typically on those lines, you will target your highest value materials like your metals or your high value plastics, PET.
Thank you. And I have another question. I know
Sure.
that those waste MRFs are largely subsidized by the government still, and most of them are most of the recovery is still unprofitable, unfortunately. How far do you think we are from making it profitable, including using a robotic system like AMS?
Yeah, so since we run our own secondary sort facilities and we support our external customers, I really can answer this, but as someone who does it, ourselves. And I can say that it can be profitable. So a couple of things to really think about in the equation is making sure you're picking as much as you can, right? Your revenue is tied to tons in this industry. So you want to make sure that you're recovering as much as you can. You're recovering it into bales that have the highest value. So each bale will have a spec to it, typically an ISRI grade or something, depending on your location of like what that recipe is for the bale. And so if you're recovering as much volume as possible and it's at your highest purity, that's going to give you the highest revenue. And then if you're doing it in a way that reduces your cost per pick, that's reducing your cost, and now your margin is really good. And that's where technology can really help keep that as controlled as possible. Certainly humans can get there, but the human cost per pick is really high. And so a robot picks at about 80 picks per minute. A human in a best case will be about 40 picks per minute, typically more like a 20, 25 picks per minute. I myself tried picking on a line once and I was at 10 picks per minute. It was really bad and I got super dizzy. So I am not going to work as a sorter, but I'll make the technology instead. So really, I think those are really your levers, is all about, volume recovered, reducing your cost per pick. The other side of volume recovered is if you're not pulling it out to sell it as a good, you are having to pay to landfill it. So you get a double whammy effect of now you get revenue and you're avoiding cost. And so I think, where facilities are not profitable, it's usually a combination of are they getting good material in? Are they recovering everything they can out of it? Are they sorting it into the most profitable bales, and are they keeping their costs low?
Thank you.
Yeah, thanks for the question.
Couple quick questions, Amanda. Great presentation. Curious to get your thoughts on Delta versus 6-axis robots, which have, I guess, theoretically, they have higher degrees of freedom. Have you tried with 6-axis like FANUC robots? Just curious.
Yeah, they are much slower for these applications, and also because of just the different materials that you can come across. They'll have lower loads that they can pick. So we've looked at everything. We've done gantry, we've done, like you name it, we've done it. And we really settled early on this Delta style for, you want longevity. Any customer putting these things in wants to make sure it's going to work, ease of maintenance, right, and just overall performance.
Got it. Okay.
That cost per pick goes lower when you get a higher picks per minute.
Makes sense. And you had mentioned perf and chemical recycling.
Yeah.
Just curious, like with RGB cameras, are you able to get specific on the resin code type to facilitate chemical recycling, which typically tends to be very sensitive to contamination?
Yeah.
Or do you envision needing additional sensing modalities in addition to RGB?
Yeah. So with our perfs today, so these are the plastic recycling for anybody who's not familiar with that term, and they are trying to remove contaminants that in a chemical process would really contaminate what they're trying to do, and like totally would change the chemistry on it. We tend to be pulling out very visible contaminants from those lines today. You're absolutely right that if you have something like a thermoform, which can also have PVC, we cannot detect that through AI unless the form factor alone is something indicative where we can say, okay, it looks like a thermoform, but because it looks like this thermoform, we know that that one's, PVC content. And so yes, in some applications, having NIR or some other sensor modality absolutely is a benefit.
Got it. Thank you.
Yeah, thank you.
Great. Thanks for the questions and thanks for that talk again.
Yeah, thank you.
Maybe we can move forward with our schedule of talks, and I'll remind everyone that we do have some additional time at the end for more questions. So yeah, if you haven't gotten your questions answered, we do have some additional time. Okay, so up next we have Ian Goodline and Ethan Volko. Ian and Ethan are co-founders of RStream Recycling, a startup company for automated waste sorting. Previously, they both received their master's degrees in mechanical engineering with a concentration in robotics from the University of Massachusetts at Amherst. Their work at RStream has received recognition both as finalists of the university's 2021 Innovation Challenge, also in the Boston Business Journal's 25 under 25 innovators award. I think Ian is presenting. Correct me if I'm wrong. I'm sorry.
It's going to be both of us.
Both of us, both of you. Cool. Sure, go ahead. Thanks.
Great. Well, thank you for the introduction. Yeah, we're RStream. We're working towards hands-free waste collection to capture more sustainably. Yeah, you can go to the next slide. So hi, everyone. My name is Ethan. I am the co-founder and chief technology officer, and I'll be presenting with Ian, who is the CEO of RStream. We're both actually mechanical engineers as our background, as was just mentioned, but we started this company as a hardware and software solution to frontline waste. And so that's how we ended up actually doing some research in the AI and computer vision space. And we're based out of Greentown Labs in Boston. I'm really excited to be sharing with everyone what we're working on right now. So a little bit about what we're going to talk about is the circular economy, which Amanda just did a great overview on, as well as the opportunity that we're kind of focusing in on, our solution for that, and the specific challenges that we're facing, as well as our approach to those challenges and how we're implementing some solutions and our goals for the future. So by now, we all know that the circular economy is at center stage. We've seen domestic ESG policies, environmental and social governance, where we have companies and municipalities really prioritizing their impact on society. We've seen foreign policies that have cut supply chains internationally, and we've also seen domestic policies that are attempting to facilitate the circular economy stateside. And so lots of work has been done to focus on how we can improve recycling efficacy when materials get to the recovery facility. But we wanted to take a different angle and investigate how these macro trends are impacting the sites who are trying to recycle. So the clients of waste management, you can think about that as a UMass Amherst or a stadium, like an NFL stadium or something. And so when we began this project, we started with the closest site we could find, which was UMass Amherst. And so we did the local I-Corps program there, and we got to start talking with some people who deal with the waste every day and trying to improve the performance at these universities. And so during the program, in speaking with these sustainability teams, we learned that these macro trends had made recycling more expensive, yet there was still pressure on them from their stakeholders at a university to make recycling more effective. And so sites wanted to address contamination, which is simply just trash or recyclables ending up in the wrong bin, but they had a limited capacity to do so. And so some even resort to picking waste by hand. At college football stadiums, they'll sometimes hand sort waste after games. And it was actually more common than you might think, just to try to get their contamination rates down so that they can make some improvements. So ultimately, these sites were stuck with costly programs, a desire to improve them, but no way to do so. And so drilling down a little bit more into the problem of contamination, we were able to find out that contamination actually costs the US recycling system at least $300 million every year to quantify that mistake that's being made by consumers at the point of disposal. It's that big of a problem. And that for haulers, from their perspective, they're dealing with waste that's twice as contaminated as they want it to be. Their goal is to be under 10%, while they're receiving over 20% on a consistent basis. And so that kind of comes full circle, and you can understand why the cost to recycle has gone up significantly for these sites. And so this research kind of led us into what we came up with as our solution, which allows for, which is technology that automates collection decisions. So it's going to make that decision of trash versus recyclable or compostable. And we do this through an all-in-one waste bin. So we can accept all different types of materials, whether that's trash, recyclables, or compostables, and sort them into their desired destinations with a roughly 90% accuracy, so that you can still work with your standard hauling contracts. For the sites, that's really important because they definitely want to maintain those relationships that they have, because waste services are essential. And so we do this with a combination of hardware and software, hardware that can intake and control the flow of a bulk deposit. You can think about a whole entire bin of recyclables that's being dumped out. That's what we have to deal with. And robust sorting so that we can handle that variability, because while it is rigid recyclables, it could also be food waste or something that is largely deformable or highly random. So the physical sorters that we're using have to be very adaptable to different scenarios. And on the software side, we're using visible spectrum computer vision to identify the form and the materials that we're working with. We're trying to continuously improve the accuracy with things like active learning, and we're working to be able to provide insights to the stakeholders in an industry that's typically been largely murky, try to provide some transparency for the sites that our system is installed at. And so now Ian will kind of get into a little bit of the specific challenges that come along with this.
Awesome, thank you, Ian. Hi, everybody. I'm Ian. So the implications of implementing computer vision at the forefront. Now we're talking about an entire bin being dumped onto conveyor belts. This is more similar to the beginning stages of a recovery facility, something that Amanda referenced has challenges associated to burden depths and high variability. So in our case, we have a unique hardware setup that can facilitate the sorting and identification of these things. But as a result, we have a high level of clutter still, and unique classes, as well as a just unique background in general. So we're in a situation where we, like AMP had at the very beginning, are looking to construct a very sizable data set that can be accommodating of the amount of variability, the amount of classes within, to make sure that we can still facilitate recycling, get accurate classifications and localization, and doing so for a segmentation data set is going to be extremely expensive. So this is one challenge that we're facing as a new implementation. Additionally, we deal with the same challenges of generalization. Interestingly, all of these water bottles come from the same manufacturer. These are the sort of things that happen as we're looking to shift between domains. While there is a broad variety of material recovery facilities, which a model might have to specialize to, implementing this at the clients of the material recovery facilities creates more and more branches, where the model may be fine-tuned to improve performance, but as we're looking to shift between domains, it's essential that we're able to do so effectively. If our first client is in Boston at a sports stadium, and our second client is at a university in California or overseas, or et cetera, being able to construct our data set in a way that we can then generalize out and rapidly install is essential for our commercial viability. And the last one that's really significant to the collection problem, as opposed to industrial sortation, is that we're facing an extremely high variability. This comes in the form of introducing trash at higher rates than you would see in a material recovery facility, as well as biomaterials or alternative compostables. There's an ever increasing amount of these in an effort to provide sustainable alternatives to polymers. And in fact, they create increased challenges for consumers to make decisions. And if we're going to be making the decisions for consumers as to where things are to be going, we're going to have to deal with a broad variety of classes. To get into a few of our technical challenges, and while there are many, our main approaches right now for research are focusing on the labeling and data manipulation. So with constructing our initial set, doing so efficiently, using semi-supervised learning to rapidly construct the data set. Additionally, when we're implemented in our first few sites, when we're responding to new objects or evolving environments, say a university changes their pouring rights contracts from Coca-Cola to Pepsi, there's going to be a domain shift. So we'll have to deal with things like few-shot learning for new things being introduced and active improvement in our system. On the data manipulation side, we're looking to improve our data set through augmentation techniques. So we're exploring classic ways to augment data, such as position or color augmentation. But additionally, we're we're really interested in several of the topics that were discussed today or throughout the conference related to more advanced forms of augmentation, whether it be the application of synthetic data in the long run. These are the things we're researching under the NSF. And on the next side of it is for data manipulation. How can we perform domain shift efficiently to help our models start up effectively with limited relabeling or retraining in new environments? And this is a practical limitation of decentralized deployment. By enhancing our generalization through approaches to domain adaptation, we can decrease the implementation cost. And for somebody like us, that's really important because it lowers the barrier for entry implementation cost to deploy our stream in a broader variety of places, not just NFL stadiums with billion-dollar owners, but underserved communities, international environments where we need to be able to implement things with limited upstart cost. Our current objectives are we're pursuing pilot partners to diversify our data set and test our generalization. We're working with the ever-growing list of universities and stadiums who you guys may be the universities who we're working with right now. We started really with the problem first in an approach similar to Colorado's advice. And the next piece that we're working on simultaneously is building our technology stack. As Amanda recommended for AMP, we are also interested in seeing how similar access to data can be trickled down to the actual sites. So who have independent sustainability programs, who are tracking key performance indicators for their programs, they want to figure out if their consumers are disposing of things properly and to be able to report back to their own stakeholders. And lastly, a shameless plug is that we're in the middle of looking to hire people and find collaborators to work on several of the technical aspects in software and data science to get through this first pilot. And in the next few months, we'll be doing the following, including a fundraise and accelerating through partnerships. So we're excited to connect with those of you who find this to be really interesting or think you might have unique solutions to the problems that we're facing. And thank you. We can take any questions.
Thanks, Ian and Ethan. Oh, yeah, yes, go ahead.
Oh yeah, really cool direction, fellas. A couple of quick questions. So, are you guys planning to manufacture the hardware yourself?
Yes. So this is hardware that came out of our own research, and it in itself is a unique aspect of our stream.
Gotcha. Very cool. Are you guys doing this or spinning up at scale right now, or are you guys currently like building these?
Yeah, we're in early stage startup right now, pre-commercial, looking to finalize our first pilot agreement, and in pursuit of more at the same time, so that we can test some of these domain adaptation concepts because it's essential to our business model.
That's very cool. And I ask the robotic startups at Berkeley kind of the same question. A lot of times, they either try to use their own or somebody else's hardware or only need to build a select number themselves, so they don't have to spin up the manufacturing pipelines, which are very slow. That's a cool direction. And my second question, just out of my own curiosity, then maybe we can get back into the more of the science. You mentioned there was like $300 million of lost something. I don't know.
Yeah, that's an estimate by the Recycling Partnership for the impact of contamination. So when in an industrial recovery facility, they're sorting out residue from the recycling stream, the estimated impact of that on the financial model for the recovery facilities around the country. So that's like labor. Yeah.
Is that through labor or through the actual like loss?
Labor, transportation, machine use and upkeep, things like that.
Very cool. And so if our stream takes off, is that the 300 million? It'll, boom, it'll save that.
Yes, exactly. Our vision is that we can use our stream technology to increase capture rate, as well as go from a 20% contamination rate down to a 5 or sub 5.
Right. Yeah, that's very cool. And then in these sorting facilities that we've been talking so much about, could that also replace a lot of that labor too? Is there a larger labor cost there than 300
It
million?
could decrease some of it, particularly the labor that takes place on the very front lines, concerned about hazardous things, which may be entering their recovery facility, which would otherwise damage equipment. So that's a sort of thing where having some level of almost quality assurance of your inbound products, to continue the analogy of a circular economy. If there are robotics implemented upstream, then you know that what you're getting is going to be wholesalable and that it's going to be of a high enough quality, safe. So there is some sort of effect on the labor needed in industrial situations, but we're not looking to bypass those recovery facilities because they play other roles in logistics, aggregation, and marketing of the materials.
Yeah, the other thing about that upstream data is it can help with some of the logistics aspects of the hauling companies like tasks, and like in terms of scheduling pickups and all that kind of stuff as well.
Yeah, that's a very cool space. Thanks so much, fellas, for presenting.
And Ethan, I think you mentioned this, sorry, I missed it. What are the main verticals that you're looking at in terms of deployments, like which industries primarily?
Yeah, so we're looking at what we call high traffic venues as a place where we can fill out or prove out our technology, just because they have a really concentrated like waste stream, and it's also highly contaminated. So they have the potential to have a really positive impact and save a lot of money, but they're not able to capitalize on that. So that's where we're focusing out to try to get our first systems deployed.
Makes sense. Thank you.
All right, thanks again, Ethan and Ian, and everyone else for the questions. It was a very interesting talk. Next up, we have Sujit Sanjeev. Sujit leads efforts related to leveraging Google's data and technology to help solve waste management and plastic pollution. Sujit has a master's degree in computer science and has worked as a software engineer prior to his current role at Google. We're eager to hear to the talk, Sujit.
Great. Can you all hear me and see my screen?
Yes.
Okay, great. So before I jump in, just some context on, I guess, how we started entering the waste management area in general. So our VP, Emmanuel Sake, he went on a sailing trip from California to Hawaii. And as part of his sailing trip, I think out of 8 days, 3 days straight, he just sailed through trash in the Pacific Ocean through the Great Garbage Patch. And that kind of experience transformed him. And when he came back from Hawaii, he was like, hey, we should do something and play our part in help solving the problem. And he kind of spun our team together as a passion project. It wasn't really like a very strategic decision as a product area within Google. It's more of a passion project for our VP. So he kind of spun a small team together, and we just put our heads together to see how can we help. And naturally at Google, like machine learning and AI tends to be our strength. So we thought like, hey, let's put our heads together and see what we can do about it. Prior to this, none of us had any experience in the waste industry. So we are by no means experts in the waste industry, but we just have a passion to kind of solve this problem together. That's kind of the context. So we've developed a model called CircularNet, and I'll walk you through a brief introduction to it. But we strongly believe that waste management deserves a tech tune-up. And we mentioned free here because going back to the previous questions that Dina asked, existing solutions are very kind of costly for companies, especially in the emerging markets, to be able to afford. So we're trying to make it as much as no cost to low cost as possible. And the challenges that we see in the ecosystem is kind of fabricated here. So firstly, from a consumer standpoint, there's a lot of confusion, which I guess what our stream is trying to solve for. Like there is no universal source of truth on how, where, and what to recycle. And once it enters the bin, it's subject to a lot of contamination, as we all know. And the third pillar is kind of a lot of companies in the space, but it's all very fragmented and siloed. Like each company captures data set, trains their own model, and then deploys in their robotic systems. So it's very siloed and fragmented. And people tend to like reinvent the wheel again. And mechatronics, which is robotics integration, is again costly and trained on proprietary data sets. So these are challenges that we see in the ecosystem. So we are trying to see how can we optimize and help and play our part here. And our goal is to develop an open source machine learning computer vision model for deployment across the waste management ecosystem. And when I say ecosystem, I pretty much refer to this slide over here, where starting from the consumers, sometimes unfortunately ends up as litter on streets, and then it goes to smart trash cans, smart haulers, and smart MRFs. So this is what we mean by the ecosystem. And our eventual view is that can the model be used for consumer education? Can it be used to detect litter on streets, smart trash cans, haulers, and MRFs? For the streets, we actually worked with the United Nations to develop an open source model for identification of litter on streets. So that's kind of already done. But our eventual vision is that technology will have a role to play across all of this. And in terms of how our approach is different, firstly, it's open source. The model, the training scripts, etc., it's already on GitHub, and it's powered by TensorFlow. And we do instance segmentation. So it's not object detection, it's not semantic segmentation, but we do instance segmentation. And we believe that this will help robotics be more efficient because the robotic arm now has information on the geometry and the contours of the object. It's not just like the bounding box and the centroid. And it runs on our Google Cloud, which is arguably one of the most sustainable clouds in terms of power consumption, etc. And we are striking partnerships globally. So it's not a very regional focus. We are focusing on emerging markets as well, equally, and in developed countries as well. And the more people share and collaborate and make it a more robust solution, the better it gets. And we're starting with MRFs. Out of our broader vision, we're starting with MRFs right now because that is the highest ROI that we see for the immediate future. And the reason I think Amanda touched upon this, MRFs are moving rapidly from manual to, I think right now it's in a human-machine symbiosis. That's the way I like to call it, where humans work together with robots, but the future will be fully automated, where you have a software layer orchestrating all operations of a MRF together. So to train this model, we are identifying intervention points. I think Dina asked a question like, is it where do you install the cameras? Like, is it pre-sort, is it pro-sort, what's the burden depth, etc. So a lot of considerations in identifying where to install cameras. And we've been partnering with MRFs to kind of capture this data to develop this open source model. And in terms of the benefits, I think most of you are familiar, but basically giving accurate real-time insights in deploying on edge hardware, helping them identify contaminants on inbound and outbound waste streams, automating waste characterization reporting. I think Amanda spoke about like a lot of landfills, a lot of recyclables being lost to landfill that we'd all like to avoid, help in bail auditing and identifying seasonality and trends in consumption patterns, like that can help in fetching higher prices for the bales. So we have 3 models that we've developed so far, all based on RGB form factor. We don't have any additional sensing modalities for today. The first is the material type model. As you can see, pixel level instance segmentation in action here. The second model is the plastic resin type, again, based on pure RGB. And the third model is tells you the form factor, is it a bottle or a bag, etc. So these are the 3 models. It's already available on GitHub. In terms of our overall approach from a technical development standpoint, we've open sourced the model on GitHub. We plan to deploy this in the Cloud Vertex AI infrastructure. So the benefit of doing that is that anybody with a GCP account can now retrain the model and fine-tune it for their own use cases. They can just take the base model from GitHub and then fine-tune it for their own needs. Once you deploy it on Cloud Vertex, you have an API available. On top of the API, you can build all the applications and to reap the benefits that I spoke about in the previous slide. And that's it.
Thanks for the talk. Any questions specifically about today's talk? I guess at this point, sure.
Yeah, thanks a lot for the presentation. It's a great initiative. Do you mention open source? Is this currently available, the code or the data?
Yeah, the code and the model is already available. Data, we are still trying to work because there's some legal repercussions there because we are capturing data from MRF. So we're still working on, our goal is to open source the data eventually. So we're still working on it, but the code and the model is open source. It's already on GitHub, and I just pinged the link in chat.
Great, we'll have to try it on our data.
Yes. Again, so we are continuously training the model on new data sets as we capture additional MRFs. So the base model that you see on GitHub is just from a very limited data set. So happy to kind of collaborate offline and give you the more advanced model, which is being continuously trained upon. We haven't yet published that.
That sounds great. Yeah, we'll reach out.
Sure.
As far as testing and validation, is this mainly happening with data from recovery facilities right now, or is it happening at different points in that spoke?
Yeah, right now we're just hyper focused on MRFs, but hopefully, like even for use cases like yours in our stream, right? Hopefully, you can take this model as the base model and build upon that, and deploy it in additional facilities in the circle that I showed. But right now, it's all MRFs focused. And again, when we move from MRF to a waste bin or a hauling truck, it's a domain adaptation challenge in a way. So I think all of the solutions being discussed here will be very helpful.
Absolutely.
Yeah, thanks again for the talk and all the questions. We can probably now open it up for questions to any of the speakers, have a discussion if that leads to if it leads to that from any of the questions. In our schedule, we have up until another up till another half an hour. Yeah, and feel free to stick around and yeah, go ahead if anyone has any questions for the speakers.
Hi, I have a question. This is for Jehan. And it's about using the convex architecture. I was curious if I caught it correctly, that the motivation for using that architecture was because it was trained on ImageNet 22K or 21K, the larger ImageNet version, or was it also something about the architecture itself? So in other words, would you expect like a vision transformer trained on that same pre-training data set to perform similarly?
Thank you for your question. We've got considered the other three backbone except CommonX, which are Vision Transformer and Swing and Twins. However, the best performance is CommonX in this data set.
Okay, thank you.
Okay.
So it is for ImageNet 22K.
Thanks. Okay, I have another question. This time for
Right.
Colorado, if he's still around.
I don't see him.
I think he might have dropped off. Okay, I'll ask him.
I have a question to Sujit. As we've all probably seen that in many applications of the AI for the environment, at least that's what I got from my conversations with the folks from other areas that work in the AI for environment and climate. One of the biggest bottlenecks is actually getting enough data that will introduce a lot of variety. And I really like your initiative, Google's initiative in collecting. Seems like such a diverse data set. I'm not sure you have the exact statistics on how much data you have, but it's a great initiative in making research and waste sorting more accessible in open public. So my question is, Is this the fully nonprofit project from Google, or are you planning to somehow also incorporate it or sell your solutions at some point?
Yeah, right now, as I said, this came out as a pet passion project from our VP. So it's not like a really commercial, well thought out product strategy. So right now it's just free. It's open source under the Apache license, which allows anybody to use it freely for commercial or for research purposes. So for now, we don't have any plans as such. It's just like a free altruistic project. And our goal is to really like accelerate innovation in the waste management ecosystem. And what we see is that in emerging economies, it's really hard for them to be able to afford expensive technology. And our goal is to like democratize access to AI and ML in the space globally.
Thank you.
Actually, I have a follow-up question to that. So in terms of democratizing this kind of technology, I can see how, having a webcam or having a camera installed, that's a relatively inexpensive way that someone in an emerging economy could be doing this. But what about the robotics aspect of it? So if we wanted to truly automate recycling, seems like the robotics, the hardware solutions, not so affordable, perhaps? What is your view on that?
Yeah, totally agree. Right now, we are focusing more on the vision, which is kind of the eyes and the brain part of it. But we are looking into some cheap robotic solutions as well. I think you all know the robot operating system, which is kind of open source, and people can plug and play into that as well. But you're still in the early days, very early days in our journey here, just starting with the vision portion for now. And the benefits that I spoke about in the deck can all be reaped with just the vision and analytics. But obviously, if you add robotics, it makes it a much more useful solution, especially in emerging economies. But there is kind of a paradox there as well, because in emerging economies, they tend to employ people that tends to be cheaper. There's no labor shortage like what we see in the US over here. So for them, a software-only solution tends to meet the need compared to markets like in the US, where there's a labor shortage and you need robotics as well. So there's a bit of a mismatch there in terms of the product market fit. But something which we want to look into as well, hopefully make it more accessible and democratize access to that.
I'd like to jump in a little bit too about the cost of robots. You want to go first, Ian?
You first.
Okay. So typically for facilities that own and operate their own, facilities, so like a Waste Connections or WM for US-based recyclers, they want to own the assets because they can depreciate them. So there's a cost of it up front, but then they're spreading that over time. And so that, the life of these robots, if you're picking a good robot that lasts for a long time, not something that's going to break after 2 years, and, everything has like a disposal versus longevity and cost trade-off to it. It tends to work in their favor. And so when we are talking to customers about showing that return on investment, in most cases, we can make the story alone with labor replacement. And showing that it's actually cheaper than your labor when you look at a certain period where they're trying to get the payback period within that. And then anything around increasing how much you recover and increasing the purity of those bales for higher revenue is gravy on top of that. But just with the labor replacement alone, the robots are already at a price point where they show that it's more effective than human sorters for US, Europe, and UK. So the point still remains that in other locations where the cost of labor is lower, that equation is flipped.
And where I was going to head with the concepts being in underdeveloped situations, which is a similar cost situation to decentralized applications. In addition to the hardware cost of robotics, the hardware cost of computing is a significant cost. So if you want to implement something at a bin level and you need an onboard computer to deploy an edge case, then this is the utility of making sure that you can do these deep learning detections in a resource efficient way.
It's a really good point. And as I was thinking just a little bit longer too, there's a little more than just cost of labor. These are dirty, dangerous, repetitive jobs doing this sortation. And so there is, a human safety element to it, and very hard to put a price tag on that.
Yeah, actually, we started working on this project as part of an NSF-funded project that involved it still involves, is still going on. A bunch of researchers, including folks from WPI and from Yale, roboticists, and also recycling experts, and AI people like me and myself. And the purpose of that project was to look at the future of work. It's the NSF Future of Work program. And so our pitch was that this is like you said, a dull, dirty, and dangerous job, and maybe not a job that we want to necessarily protect from automation. But we did want to see, how robotics would affect these kinds of jobs, and so we kind of went at it from that aspect. But then we quickly found there was very little data available for us to study things, from the computer vision side. So we ended up collecting the data first, as it usually goes in these research projects. You got to get your data first. But yeah, I have been to an MRF, and I can testify. It's like seems like a very kind of sort of unpleasant job for a human. It seems like it's pretty well suited to a robot to take it over.
We like to joke that it smells like money in there, but it just, it's that organic dust in the air. And it's amazing that before COVID and before we all got used to wearing masks, people in those facilities would not wear masks. So they were just breathing in that dust all day long. It's just incredible. We've seen dead animals, we've seen organic matter, chemical spills, needles, in the line, and that's where it just is so dangerous, and we can do better than that.
And I guess the elephant in the room is batteries, right? MRFs catching on fire because of
batteries.
batteries. Yeah, those are great. And also, I guess the distinction between clean MRFs and dirty MRFs, which process landfill, the black bin, and organics and stuff. Yeah, the stink is a huge difference.
Yeah, the hazards are actually the same across a dirty MRF and a primary MRF. It's just the frequency of the hazard increases at a dirty MRF. And if you're not familiar with that term, there's a really great YouTube video for a dirty MRF in San Jose, California, and it'll walk you through how the facility is set up and what they're separating at one point in time. Plus, like all great videos, it's got like really cool music behind it. So definitely recommend checking that one out.
I've actually been to that one, Amanda.
Oh, nice.
had to wear double masks, but I've been there.
Nice.
Yeah. The first time that Ian and I went to a MRF, the plant manager showed us a video of a propane, like a small, camping canister exploding inside of a baler. That was pretty terrifying. So yeah, I can definitely agree with what everyone's saying, that it's a pretty crazy place.
And he said that they fill up a trash barrel worth of 1 gallon propane tanks before lunch every day. Yeah. And alternatively, they would explode in balers or various places, fully light things on fire, degrade the quality of the recyclables that they can't wholesale, put workers in real serious danger. And this is a relatively average or below average MRF size. So at a real serious municipal collection center, it could be even worse.
Yeah, there's kind of 3 main hazards: the propane tanks, aerosols, because they'll also go boom, and then batteries, because they burn. And the batteries, it'll crack, and then it's exothermic, and it'll typically be on your tip floor or in your fiber bales, where, by then it gets hot enough, and then, and there's a video that just came out last week. Unfortunately, one of our robots was caught in a fire, but everyone was safe at the facility, so that's what matters most. And within 10 minutes, it went from, a smoke signal in the tip floor into the entire thing was burned down.
In fact, the MRF, which is just 10 minutes from where I'm sitting right now, which processes the waste from my household, caught fire a few years back. I think a couple years back. There's a huge fire, and actually their insurance rates, etc., went up. So it's very tough for them to operate in this environment as well, because the insurance companies charge them fairly high once they have fire.
So here's your public service announcement. Please never put batteries, propane tanks, or any electronics in your curbside recycling. Please bring those to the proper electronics recycler.
Also medical needles as well. I've heard horrifying stories about those.
I have learned so much about recycling since starting this research project. I have a question for all the speakers in general. Where do you see the academic AI research community being able to contribute to this problem the most? So for myself, my lab, future students, or folks that want to get involved on the academic side, what do you think are interesting problems that we could push for? You know, things that are not immediately already working, perhaps, but something further out on the horizon that you think would be an interesting contribution for the academics. And just feel free to jump in, anyone.
I have two I can immediately throw out there. So curious to hear what everybody else has. The first is around the ontologies. And so, you know, GTech has published one. We actually worked on you. So I don't know, Sujit, if we worked with you directly, but we've worked with GTech to outline that. And there's so many different ones coming out with all the different EPRs. So Cal Recycle has their own, and Ontario has their own, and UK has their own, which is different than EU's because thanks Brexit. So, you know, I think just how to make one neural network adaptable to all the different ontologies in the world is one thing to think through. And we're, you know, putting together our own response to that, but like let's figure it out together as, you know, humankind. The second is around just wanting to be able to deploy, you know, bigger and faster neural nets out at the edge. And so maybe, you know, a little bit more of a hardware academic research on just how do we make that, you know, constantly support itself, you know, without adding all the issues that can happen.
Big plus point to both of them. I think on the ontology portion, like we have our own, AMP has their own, I guess Ethan and Ian will have their own ontology and taxonomy. I guess a common language, I think is a good starting point for everybody in the industry to collaborate. And I think Kate, you touched upon this as well, like democratizing access. Like the moment we reach out to like emerging economies, everybody wants this, but they just can't afford it. So anything we can do to democratize access while obviously being sensitive to for-profit companies to not like, you know, disturb their business model, that's equally important too. But that's a tricky problem to discuss and solve. I think it's well suited for the academic community.
And it's been touched on, and Amanda brought it in the direction of letting us deploy things bigger and better, but also smaller and more agile, being able to deploy things that are derived from these very complicated algorithms and send them to somebody's cell phone in a remote location so that they can make decisions, or more likely deploy them on a small onboard edge case that's like actually situated in the disposal location. These are really interesting problems that could be helpful for accessing a broader variety. I mean, we spoke about 50% of people have curbside recycling automatic, and that's in America, a super industrialized location. What does somebody do when they're in a highly remote situation where the economics don't make sense between transportation, sortation, aggregation, wholesaling? It just gets burned or landfilled or thrown into the Great Pacific Garbage Patch. So being able to allow us to deploy these models for low scale cases where they can aggregate high volume things and extract the resource value and have the sustainable impact is significant.
Thank you. Yeah, that's a tough challenge. I think one of the issues for academics is just accessing the data so that we were able to work on solutions. So that's why I'm, you know, I've been pushing to release this data that we've collected, and I'm very happy to hear that Google is planning to release some data. So hopefully we can make progress towards these goals as a community.
Yeah, and we have some, you know, commercial terms around the use of our data, but Kate, happy to follow up with you offline and see if there's something that we could do to put together some sort of project together.
Great. Yeah, that sounds great. Will do. Okay. Maybe we can start wrapping things up. Want to be respectful of time. It's pretty late here, getting late here. Are there any other last comments or questions?
I would just like to thank my team members and all of the speakers and all of the teams that participated in this challenge. It was great hearing from you, and yeah, I just massively enjoyed talking with the fellow people who also wasted days of their life looking at trash. Yeah, thank you very much.
Oh, and of course, the winners, will be sending you electronic gift certificates. We can't be there in person to give you the winnings, but we'll be sending them via email. And thank you so much for participating. Congratulations. And yes, thank you so much, Dina, especially for organizing, and Samarth and Dayala and Piotr, my students who've worked hard to make this challenge possible.
Yeah, thanks for organizing. This is great.
All right, thanks everyone.